Um, so, why are nuclides radioactive? And why do they undergo different types of decay? Those are difficult questions to answer. So, what is a nucleus? A nucleus is a collection of nucleons. And so nucleons are the particles in the nucleus. So those include protons and neutrons. We get tired of saying protons and neutrons all the time, and so we can call them nucleons altogether. And those nucleons are bound together by what's known as the strong force. This is a fundamental force of physics which acts at very short distances. And so the stability of the nucleus is a balance between the repulsive force between protons, because two like charges, two protons, are going to repel each other, and the attractive strong force between all nucleons. So we've got a balancing effect there. So this graph, rearrange my setup here so I can see what I'm doing. This graph depicts what's often called the valley of stability. And so what they're graphing here is number of neutrons versus number of protons. And the green dots, they look kind of gray to me, but those dots are stable nuclei. And so they form kind of a line through here, and this region here is called the valley of stability. So it's kind of like when we talk about things being lower in potential energy, being stable. Oops. So this would be the valley where everything goes down and becomes more stable. So we can look at a trend in the ratio of neutrons to protons. And so this stable ratio starts out at 1 to 1, so down here. So like carbon 12 is stable. It has 6 neutrons and 6 protons. And so the ratio is 1. But as the elements get larger, this is the line where n over z equals 1. We see that this curves up from that line, and the stable n to z ratio gets larger as we go along. Here it's 1.25, up here it's 1.5. And so the type of radioactivity that's emitted depends in part on the n to z ratio, because the radioactive particles are emitted to make the nucleus become more stable. Anybody have any questions? Okay. So we can make some educated guesses in predicting the type of radioactivity by looking at that n to z ratio, the number of neutrons to the number of protons. If the n to z ratio is too high, we've got too many neutrons, and so those nuclides will tend to convert neutrons into protons, and that happens via beta decay, the emission of electrons. So neutrons can turn into protons. That lowers the ratio, and the nuclide becomes more stable. If the ratio is too low, then we've got too many protons, and so they will tend to have emission or activity that converts protons to neutrons. And so this can happen by positron emission or by electron capture. Alpha decay can also raise the n to z. ratio, but the effect is smaller than for positron emission or electron capture. So there's two methods we can use to predict. One is we can consult figure 20.5. It's 21.5 now, but we can look at that graph, the valley of stability. So that's great if you happen to have that graph available. We can also compare the mass number of the nuclide to the atomic mass listed in the periodic table for that element. So on the periodic table, the atomic mass is the average of the stable nuclides. And so that's going to give us those nuclides have an N to Z ratio that's good, that's about stable. So for an example, we can look at ruthenium-112. If we find the ruthenium on the periodic table, we see that the atomic mass of ruthenium is 101. This isotope or nuclide has a mass number of 112. So that means it must have too many neutrons. So then we can predict that this will undergo beta decay to convert beta decay neutrons into protons. Yeah.
So when we're looking at that, it's wanting to become equal. Is that what you're saying?
It's not equal because with the larger elements, the N to Z ratio is actually above 1.
Okay.
But we can look at the atomic mass on the periodic table gives us an idea of a mass number that's stable for that particular element. So ruthenium is dang it. No hiding from me today. Oh, there it is.
It's under iron.
Yeah, 44. So 44 protons. So if we round this to a whole number, mass number of 101, we got 57 neutrons. And so this is 44 to 57 is the, no, I did that backwards. It's N to Z. It's 57 to 44. So that's about 1.3. If we look at this isotope, 112 minus 44 68 neutrons. So this is 68 neutrons to 44 protons. And this is 1.5 something. So this N to Z ratio is higher than this one. This one just gives us a guess at what would be stable for this element. And so we can predict that this is going to undergo some sort of decay that's going to cause the N to Z ratio to become closer to 1.3. So in order to do that, you have to either lose neutrons or gain protons or do both. and beta decay will do that. So then we're going to get technetium 112, and that's going to have a ratio of 67 to 43. No, sorry, 69. That's what happens when I don't use the calculator. 69 divided by 43. What is wrong with my head here?
Shouldn't it be 45?
Yes. Yeah.
43?
I knew there was something wrong somewhere. It's like, wait, this is going in the wrong direction. Yeah, because 43 and negative 1 is not 44. 45 and negative 1. That's RH. Okay. So now we've got 67 over 45, which is 1.49. Now it hasn't gone down much, but it's gone in the right direction. Normally we wouldn't do calculations like this, but I just want to show you how it works. We want to do something that causes this mass number to be more like this atomic number. So predict whether each nuclide is more likely to decay via beta decay or positron emission. So beta decay, we're going to increase the number of protons. And so this lowers the N to Z. Get that backwards. Lowers the N to Z ratio, and this converts neutrons into protons and raises the N to Z ratio. So for lead 192, we can look at lead on the periodic table and see that the average of the stable nuclides is 207. And so in the numerator is the protons, the neutrons. In the denominator is the protons. So this one's going to be 192 minus 82. And the stable one is 207 minus 82. And we don't actually have to do the math, but we see that this one's larger, right? So this is going to decay in a way that's going to raise the ratio. So positron emission for that one. What about lead-212? Well, 207 is still the average mass of lead. So the 212 over 82 this is stable, and this is the one we're looking at. This ratio is too high now, and so we want the ratio to become lower. Beta decay lowers the ratio. Any questions? Let's look at xenon here. Xenon 114. Stable molar mass. Stable mass number is 131. So we don't even have to look up the number of protons. Because both of them are going to have the same number of protons, and so the 114 is going to give us a smaller ratio than 131. This is the stable one. So we're trying to increase the ratio, and so then we're going to use the positron. Well, we're not using it, but we're going to predict that that's what's going to happen. Let's look at what we might do in terms of the valley of stability. Like lead 192. So lead 192, 82. So 110 neutrons. So 110 neutrons is right here versus 82 protons, just like here. And so we see that those are going to intersect out here. And so here our ratio is too small and we need to raise it. And so then we can predict beta emission. So
wait, did you say, sorry, can you go back to that slide you just were on?
Mm-hmm.
So you said we needed to raise the N2Z?
Mm-hmm.
Wouldn't that be positron, not beta?
Yes.
Positron, beta. So beta is a negative or positive.
Yeah, like we figured out over here.
Okay.
In my experience, these are a lot of things that are very similar to each other. Like positron and electrons, they're like opposite, right? And I don't use them very often, and so then it's hard to remember. So in addition to looking at the ratio of protons and neutrons, the actual number of protons and neutrons also affects the stability. And this is just kind of an odd observation. There are a large number of stable nuclides that have both an even number of protons and an even number of neutrons. There are only 5 stable ones that have an odd-odd combination. And so we believe that nucleons have a tendency to pair together, much as electrons pair together in their orbitals. And so this table is showing us number of stable nuclides. So stable nuclides with even protons and even neutrons, 157. Even protons, odd neutrons, 53. Odd protons, even neutrons, 50. And odd for both, there's only 5. That's one of those things that I wonder, who sat down and figured that out? So nucleons occupy energy levels within the nucleus, much like electrons occupy energy levels within an atom. And so atoms containing a magic number of protons or neutrons are uniquely stable, just like we observe that atoms containing particular magic numbers of electrons are more stable. So if we have N or Z being one of these numbers, 2, 8, 20, 28, 50, or 82, or if we have N being 126, any nuclide with one of those magic numbers is going to be stable. So one of the problems we did earlier talked about a decay series, where we had alpha decay and then beta decay and then alpha decay. And this happens naturally. All atoms above number 83 are radioactive, and they will decay in one or more steps. Usually they do alpha and beta decay combinations, but then the gamma decay will happen in there as well to remove excess energy. And this decay series will keep happening until you get to a daughter nuclide that's stable. And so this is what happens to uranium-238. So alpha decay to thorium-234, then a couple of beta decays. Now it's uranium again, but it's 234. Alpha decay, thorium, radium, radon, polonium, and then it can either go to lead or astatine, and then it goes to bismuth, and then it can go polonium, or I think that's thallium, lead, bismuth, polonium, or thallium, and eventually ending up at lead-206 through a whole series of decays.